So previously we stopped at basically improving and extending linear models. So we actually covered, I believe, subset selection and a little bit of the shrinkage methods. Okay. So today we are going to continue on with the rest of the ways that you would actually extend linear methods, and eventually we will then move on from linear methods to more complicated examples. Okay. Now, as I want to note, while our focus is on extending linear approaches, I just want to be clear that all the things that you are going to hear about during this lecture, things like regularization, shrinkage, and transformation of inputs, they are general to all machine learning methods in general. Okay, so it works with non-linear models as well. It works with trees. It works with neural networks. It works with anything. Okay, all right. So the first thing is about feature selection. So very often, what we want to do is to reduce the number of features, right? So instead of, say, using 100 features to, in our model, we want to instead hopefully narrow it down to the 10 that matters the most. And by doing so, what we hope to do is to introduce a little bit more bias, in the sense that now we are using fewer features to describe the data. But hopefully what we gain in return in terms of reduced variance would more than compensate for that increase in bias. Okay. Now the second reason is, of course, we are scientists, right? So for us, a model that can be a description of the data that uses 1 or 2 features is very, very much more preferred over a description that uses 10 parameters. Okay, so the simpler the model, the more likely we are to be able to interpret it, and in general, we also prefer such models. Okay, so as I mentioned, there are 3 main approaches to feature selection using for linear methods. One is subset selection, shrinkage methods, and dimensionality reduction. Okay, so subset selection is very simple. As I mentioned, you basically just take subsets of your initial feature set, and you basically keep training models based on each subset of features until you find the one that is the best model based on whatever criteria you choose. And you then basically keep doing that until you find the best subset within whatever space of features you want to look for, right? So let's say if you decide that you only want models that have 3 parameters or 2 parameters, you basically look for the best subset of 3 or 2 parameters, right? Now the problem with subset selection has always been that once your number of features go very large, then the number of subsets increases combinatorially. Okay, so basically once you go beyond, say, a few tens of features, best subset selection is not something you can do. You can, of course, do a forward or backward stepwise approach to find the best subset. That does not guarantee that you will always find the best subset, but it is a heuristic way of doing this kind of feature selection. Okay, all right. Now the good thing, the other kind of a second way in which you can do feature selection is to do what is called shrinkage methods, and this is a much more sophisticated method of doing feature selection. Okay, so the reason is subset methods are discrete, right? So you either choose to retain or throw away a feature, while in shrinkage methods you are essentially trying to apply a penalty term to basically to penalize over complex models, and that shrinkage methods are therefore continuous, right? So as you increase the penalty, the model becomes simpler and simpler until maybe a feature drops out completely, or the importance of one feature actually decreases. Okay, so the easiest way to understand a shrinkage method is through the rich regression method. Okay, so let's say you are trying to fit a linear model okay, linear regression model. And typically when you try to fit a linear regression model, you use the least squares, the residual sum of squares as basically your loss function, right? So this is this term, this very first term right here, okay? Now, in ridge regression, or what is also called L2 regularization, you have this second term, right? And this second term basically says that I'm going to add a penalty term that is this parameter lambda, and this lambda parameter is something that you have to set ahead of time, and multiplied by the sum of your coefficients squared, okay? Now, you can imagine this number, the square of a coefficient is always positive, right? So you are essentially summing the squares of the coefficients and multiplying it by some factor. And because I'm minimizing this thing overall, I'm going to actually not just try to minimize the sum of squares, I'm also trying to minimize this penalty term as well. Now, you can imagine that a more complex model with more coefficients is going to have a bigger penalty, right? Because it's the sum of beta squared, right? So the bigger the values of your beta, or the more values of beta that you have, the bigger the penalty, okay? So in other words, this penalty term actually causes your model to try to bias towards a simplification, okay? All right, so a few things to note. One, the intercept term is always not part of the penalty term, okay? That's something that you should note. And also, as I mentioned before, the inputs should always be scaled before you apply any of the shrinkage methods, okay? So typically the way that you do scaling is that by subtracting the mean of each feature and dividing by the standard deviation of the feature, all right? So as you can imagine, if all your features roughly have a Gaussian distribution, what this does is that it basically scales it to a normal Gaussian with 0 mean and variance 1, okay? So most of your feature values will then be between -1 and 1, okay? So that's the reason why you do this kind of scaling. Now, the reason you do scaling is of course also that then it takes the units that you use for each of the features completely out of the question, right? For example, if you choose to define your temperature in terms of Kelvin or Fahrenheit or in Celsius, it actually doesn't matter because of this scaling. Same, if you choose to define your weights in kilograms, grams, or milligrams, this scaling will basically render all that thing, all those unit conversions are meaningless, okay? So those units will then not affect the penalty, okay? Otherwise, because your coefficients actually scale with your inputs, you actually will not get an accurate shrinkage if you do not scale your feature vectors beforehand, okay? So I demonstrated the code. Let me go to oops, when did I sign out? Okay, so let's take a look at the notebook. So we have already gone past all the front part. I've done the subset selection, and I just want to demonstrate the recap what we are doing for the ridge regression method. So Now, this is the most important part to note about the ridge regression. You always want to scale your inputs before you actually run the ridge regression, or also the lasso regression as well. And to do the scaling, you can actually use the pre-processing module in scikit-learn. They have a class called the standard scaler that basically does what I exactly said just now. It will subtract the mean of each feature and divide by the standard deviation of that feature column. And you basically give it your x data, and then you transform your x to a z feature matrix, and you are going to fit your model using z instead of x. Okay? All right. So now, one thing about the ridge regression, remember, is that you now have an additional parameter called lambda, right? And in scikit-learn, that parameter called lambda is actually given the name alpha, okay, for some reason, okay? So what you actually need to do is to find the optimal value of alpha, all right? So in order to do that, basically what you're going to do is that you are going to run through different values of alpha, and you're going to fit many, many different models, and you're going to do a cross-validation, or maybe a simple train test split if you want. And you basically find the value of alpha that gives you the best cross-validated score, okay? So if you look at this plot, this basically is the mean square error, okay, for different values of alpha, right? So you can see that, well, when alpha is very, very small, that means that there is essentially no penalty, right? So when alpha is very small, there is no penalty. It means that it's basically your simple linear regression, okay? So as you increase the value of alpha, you start introducing more bias into the system, but at the same time, you also decrease your variance, and the overall effect is a decrease in the mean squared error, right? So you can see that your mean square error is, your test mean square error is decreasing and decreasing and decreasing until you reach an optimal value of alpha, at least in this case, of 8.2, okay? And that basically is your best value of alpha. But once you actually increase your alpha again, then basically you're over penalizing the model. So in other words, here what you have is overfitting. And once you increase your alpha too much, here what you have is underfitting, okay? So in other words, when your alpha becomes too big, your model is now oversimplified. You're actually getting not enough reduction in variance for your increase in bias, okay? So this is something you will have to do for your lab subsequently, okay? So you are going to test out ridge regression model, lasso regression models, and you are expected to find the optimal value of your hyperparameters like alpha for the model, okay? Now, once we actually find the optimal value of alpha, we can then look a little bit at what happens to the coefficients when we actually change alpha, right? Now, this looks a bit complicated, but what you just need to notice one thing, right? Which is that the bigger the value of alpha, in general, the magnitude of your coefficients decrease, right? So eventually, some of them goes very close to 0, okay? And this is basically what happens when you apply a shrinkage method, all right? As you increase the penalty on the sum of beta squared, what happens is that your model decides that, well, if this parameter... Can I silence this? Okay. Yeah. Your model is basically trying to optimize in such a way that you will try to shrink some of the coefficients, right? Until some of them get quite close to 0, okay? So this is why these are called shrinkage methods. You are shrinking the coefficients by increasing the penalty, okay? All right. Now, using the best alpha, we can actually figure out what the best equation for our bulk modulus is, okay? So this is basically the best equation for our bulk modulus. You can see that some of the coefficients are actually fairly small. none of them are 0 because in ridge regression, you actually never get to exactly 0. It can be a very, very small coefficient, but you don't actually get to 0, okay? Now, once we actually have our optimal value of alpha, we can actually redo our model with ridge regression, and this is what you get, okay? So this is a plot of the predicted bulk modulus with the actual bulk modulus, and our regular multiple linear regression, we get R squared of 0.217. The mean square error is about 8,000. But with the ridge regression, with the optimal value of alpha with ridge regression, we get a much higher R squared. It's about 0.6, and the mean square error is about 4,000, which is much smaller than what you get with simple linear regression. Okay. All right. Now, I think this is basically where we stopped in our previous lecture, all right? So now we are going to go on to some of the other shrinkage methods, okay? So the next one is one of the methods that I myself personally like the best. It is called lasso, okay? Lasso stands for least absolute shrinkage and selection operator, okay? Now, the reason why it is not just a shrinkage method but also a selection method is because in lasso regression, some of your coefficients is going to shrink with certain values of alpha, is going to shrink to exactly 0. Okay, so once your coefficient becomes 0, that means that that feature actually doesn't appear in your multiple linear regression in your linear model at all. Okay, now, the difference between lasso and ridge is basically just in the penalty term, okay? So your mean square error is, your residual sum of squares is still the same, but instead of the square of your coefficients, you instead have the sum of the absolute value of your coefficients, okay? Now you still have this lambda parameter or alpha parameter, that's basically still the shrinkage parameter, okay? And because of this formulation, what happens is that in some instances, your model gets truncated, or rather your coefficients get truncated to 0, and you basically can remove that parameter entirely, okay? So an alternative formulation of lasso is basically you are essentially trying to find the value of beta that minimizes the mean squared error, the sum of squares, subject to a constraint that your absolute of your beta must be, the sum of your absolute betas must be less than some threshold, okay? That's just an alternative way of stating the first equation, right? Again, I just want to state this again because it is very important. One, your intercept term is never part of the penalty term, and second, your inputs again must be scaled before performing lasso regression, okay? So it is both of them work on the same principle. If you do not scale your inputs, you are basically going to get the wrong results from your lasso regression, right? All right, so let's see what happens when we do lasso, right? Lasso, you basically do it pretty much the same way as you have done for your ridge regression method, right? So the lasso package, the lasso model is also under the linear model sub-package in scikit-learn. And again, you do need to find the value of alpha, the best value of alpha for your lasso regression model, right? Now, one of the things that you may need to tweak in performing a lasso regression or ridge regression is this max iter. Max iter just means what's the maximum number of iterations that you are going to allow the algorithm to try to find the best fit for your data. Because unlike your simple multiple linear regression where it's essentially just a matrix inversion, for ridge and lasso regression, they are actually using a numerical method to gradient descent method to basically find the best answer to your coefficients. Okay, so you sometimes need to increase this parameter, especially if your lasso model doesn't, the fitting of your lasso model doesn't converge within the default number of iterations. Okay, otherwise it is the same. What we are doing is that we are plotting the negative of the mean square error and we are trying to find what the best value of alpha is. And if we run this, this is basically what we get, okay? Again, just when you have close to 0 alpha, very small values of alpha, you're essentially doing a simple multiple linear regression. As you increase the value of alpha, you get some optimal value. In this case, the alpha value is 3.36, okay? And then once you increase your alpha further, you basically get an increase in your mean squared error, okay? All right, now this is actually the most critical plot in for the lasso regression, and this basically shows you how do the optimal coefficients change as you increase the value of alpha or lambda in your lasso regression, right? So similar to the ridge regression, you notice that essentially all your coefficients become smaller, okay? That is what you get when you actually introduce a penalty term. The difference between ridge regression and lasso regression, however, is that you notice that at some point, some of the coefficients are sitting on this line, which is the 0 line, right? So in other words, as your alpha increases, some of your coefficients is going to drop all the way to 0 and stay there, right? So in other words, you are removing features from your model altogether. This is why I particularly like lasso regression as an alternative to your simple multiple linear regression. So sometimes I will actually deliberately choose a linear model with more features that I need. Then I do a lasso regression to basically identify which of those features are actually the most important for my model, okay? So we can do the same thing, which is let's try to get the equation. And this is basically the equation that comes out of our lasso regression, okay? And you notice that instead of 9 parameters, for our optimal value of alpha, we only have 3 parameters left, right? So it turns out that the bulk modulus in the lasso regression framework is best described by only the melting point, the boiling point, and the square root of the electronegativity, okay? We do not need all the other features. We don't need the square of the electronegativity, we don't need the ionic radius, we don't need all the other parameters, okay? We don't need the atomic number, for instance, okay? So this is obviously a much more simpler model for our bulk modulus, right? And if we take the model and we start to plot our comparison with the predicted bulk modulus with our actual bulk modulus, we see that for lasso regression, our R square is also 0.609. Our mean square error is actually slightly smaller than what we get with our ridge regression or multiple, and is definitely half of what you get with your multiple linear regression model. So in other words, with this much simpler model, which only has 3 features, we are getting a better performance compared to our more complex model with 9 features, okay? So this is the value of doing lasso regression, okay? All right. Now, just to show you the difference between subset, ridge, and lasso, let's say if we have a set of orthonormal features, okay? Basically, what happens in ridge regression is that you have what is called proportional shrinkage, right? So in other words, all your coefficients get shrunk by a constant factor, right? And because of this, you never actually get any coefficients that truly go to a 0 value, right? You can go arbitrarily close to 0, but it is never a true 0 with ridge regression. All right. Now with lasso, basically what you have is what is called a soft thresholding, right? So we actually translate our coefficients by a constant factor. Okay. So you can see that this, if the original coefficients are along this dashed line, basically what is happening is that it is being pulled down and pulled up in both directions. and it actually has a threshold at 0, right? So in other words, once the value of the coefficients get pulled down beyond a certain limit, you essentially get a 0 coefficient. So in other words, that those features that no longer appear in your model, right? Now, best subset is of course somewhat similar to lasso in the sense that there is a threshold. You do drop out features, but it is what is called a hard thresholding. So there is no shrinkage of your actual coefficients. All you are saying is that any coefficient which has a factor below a certain, which has a contribution below a certain limit, you are essentially throwing them out. Okay, so that's what is called a hard thresholding. Okay. All right. Now, other than your ridge regression and your lasso regression, you can imagine that there are other ways in which you can define your penalty term, right? Now, another one that is very popular is called the elastic net penalty. This is basically just a combination of your ridge and lasso regression. You have your the penalty term is basically just your ridge regression penalty term plus your lasso regression penalty term in some ratio, and then you still have your lambda parameter. Now, here, of course, now you have two parameters to optimize. You have to optimize what your alpha parameter is, and you also have to optimize what the ratio between your ridge penalty term and your lasso penalty term is. Okay, so you have one additional parameter to find out what's the best value. Okay, there's also something called least angle regression that I'm not going to talk about, and we'll move on from here. Okay. All right. Before I move on, any questions regarding the shrinkage methods? Yes? No? Okay, if not, another way to basically simplify your models or to improve your linear model is using what is called derived input directions, right? Derived input directions simply just says that, well, my input matrix X, instead of using my input matrix X directly, I'm going to transform that vector space into a smaller vector space called Z of M, or a smaller subset of vectors called Z of M, and then I'm going to perform my linear regression on Z of M in that small subset rather than performing my linear regression on my entire feature space. Okay. Now, one very popular way to do this is using what's called principal component analysis. Okay. So the way to do this is basically you transform all your non-orthonormal features into orthonormal directions using principal component analysis, and then in principal component analysis, you basically get your vectors that explains in order of the explained variance. Okay, so you always have the first vector having the highest explained variance. In other words, that vector actually explains the biggest variation in your data, and then you have your second vector which explains the second highest amount of variation in your data, and so on and so forth. And what you will do is that you then say, well, I'm going to choose the first m directions rather than choose all the directions, and then I'm going to throw away the rest of the vectors, and then I will regress on those vectors. Okay. Now, I'm not going to go through PCA right now because we are going to come back to PCA within 1 or 2 lectures. Okay. But just keep in mind that this is one way to do a derived input direction. Now, the one that I'm going to go through a little bit more is called partial least squares. Okay. The algorithm for partial least squares is fairly simple. Okay. So what you will do is that you are going to compute the inner product of each of your feature vector with your actual target. So in other words, you take the dot product of each of your features with your target vector, and you are going to select, you are going to create a first transform direction by basically taking this inner product, the coefficients, and you're summing across all your input features, okay? So in other words, your first transform direction is basically each of the directions weighted by the strength of the effect on y, okay? So basically what you're computing here is effectively what is the strength, what's the strength of the effect of that particular input direction on your target vector y, okay? And when you construct this transform direction, you are saying that if that particular direction is having a bigger influence on my y, I'm going to give it a bigger weight, okay? Sounds very logical, right? Now, what you would then do is that you will regress your y on your z of 1 to obtain your first coefficient theta 1. And then you are going to then orthogonalize the rest of your vectors by basically subtracting out the inner product of your z of 1 with x of j, basically the projection of your each of your input directions on z of 1. And then you keep repeating until then you go back to the start, and then you keep repeating that process until you get whatever number of directions that you choose, okay? So the basic principle of the partial least squares regression is that you are trying to find directions with the highest variance and the highest correlation with your actual target, and then you then progressively find the next highest direction, next direction with the next highest variance and next highest correlation, and then you keep going down until you are satisfied with the model, okay? All right, let me go back to the example. Now, to do a partial least squares, in scikit-learn there is something called cross decomposition, okay? A package called cross decomposition which has something called PLS regression, okay? Now you can choose basically how many components you need. So this is the key parameter when you're doing a partial least squares. Do you want, you started out with 9 features, do you want to choose just 2 components, 3 components, 4 components, 5 components, or whatever number of components? But by and large, you typically want this number not to be too big. In this case, let's say we choose 2, and then we are going to do a cross-validation analysis to see whether we get what's the performance of our model, right? So this is a 2-component PLS, and you will see that again, just by using a partial least squares regression, we get a much improved R squared, and we also reduce our MSE significantly, right? Now, you can of course change the actual number of components. Let's say instead of 2, let's say we choose 3, okay? And now the performance has decreased somewhat, right? So our R square actually is lower, and our MSE is actually slightly higher. So in other words, probably 2 components is good enough rather than going for 3 components, right? Okay. All right. Now, so all those are methods of basically either shrinking some of the coefficients to get a simpler model, or to basically choose directions in your feature space that would actually be much more, that explains a lot more of the variation in your data, such that you actually can get a simpler model with fewer feature vectors, okay? Now, in many instances, it is very unlikely that the true function, which is basically whenever you do a machine learning model, you are essentially trying to predict a target variable y from an input variable x, right? And it is very unlikely, all right, in most instances that that true function is basically a linear model, okay? So in some cases, linearity is a reasonable assumption. So for example, if you look at a first order Taylor series expansion, if you are about the equilibrium point of A, so your f of x of A is basically just equals to f of A plus the derivative of f with respect to x A x minus a, and then the second derivative of a divided by 2 factorial x minus a squared, and so on and so forth. And you can say, well, if my deviation is fairly small, right, x minus a squared is very small, I can ignore all the terms other than the first one, and then essentially I have a quasi-linear model with respect to x, right? And this is a very, very common assumption that we make whenever we are doing science, right? So for instance, how many of you have taken mechanics of materials before? No? Simple elasticity? No? Hooke's law? Anyone knows Hooke's law? Everyone knows Hooke's law. Okay. Whenever we think about Hooke's law, right, we are thinking, well, if I apply a force, the force is equals to just a constant multiplied by your displacement, right? That's basically Hooke's law, right? In reality, Hooke's law only applies when you have a very small displacement from your equilibrium tension, okay? If you actually have a very big displacement from your equilibrium position, your linear Hooke's law actually doesn't apply, right? But within a certain limit of your deviation, linearization actually works, okay? So in other words, linear models can work under certain limits and assumptions of the system that you are interested in, okay? But more frequently, what you want to do is to basically have the flexibility to basically model more complex relationships between your input and output, okay? All right, now this is the general concept, right? So instead of modeling it as a linear function of x, I'm going to model it as a linear function of some transformation of x, right? So this is basically what is called a linear basis expansion of your feature space, right? And the key whenever we are doing this kind of thing is basically the choice of the basis function, right? So in other words, what kind of functions do we choose to transform our x input such that we can actually have flexibility in modeling the relationship, right? Now, these are some examples of different basis functions that you can use, all right? The simplest one, which we already did it for our bulk modulus example, is to just do a polynomial expansion, right? You can imagine Taylor series, right? Instead of stopping at the linear model, what if I want to incorporate x squared terms or x cubed terms, right? So I will basically take powers of x. So that's one potential kind of transformation that we can use. Of course, as you increase the number of terms, increase the degree of the polynomial, the number of terms actually also increases exponentially. So for example, once you actually get to an x cubed term, you not only have your x cubed term, you have your x squared times x1 squared times x2 terms, and so on and so forth. You basically have combinations of terms, right? So whenever you have p variables, essentially you have order of p squared square and cross product terms in a simple quadratic model, and once we get to a degree d polynomial, we have order p to the power of d, okay? Now, you can also do other kinds of nonlinear transformations, okay? So square root of x, that was something that we did for our electronegativity and ionic radius. We can also imagine that we can take the log of some of the variables. We can also take the exponential of some of the variables. Again, this is something that is very commonly done in material science, okay? So, for example, your Arrhenius relationship, right? Reaction rate equals to exponent e to the power of minus some energy over RT, okay? Now, how do you figure out what your E is if, let's say, you have temperature and R? You basically take the log of R and you have minus, then you basically have log of A minus E over RT, So in this case, you're transforming the target, and you also have to transform the input to 1 over t, but this is effectively, again, a linear model, okay? So log and exponents are, again, very, very common type of basis transformations that we use, right? You can also do what is more sophisticated, which is called a piecewise division of regions. We are going to come back to that. That's basically cubic splines, okay? You can also do radial basis functions. This is especially common if you are doing things like electronic structure calculations or quantum chemistry calculations. Very often, for example, when you try to solve the Schrödinger equation, you have to assume that your wave function takes on a certain you have to basically use a set of basis functions to describe to expand your wave function, and very often that choice of basis function is a radial basis function type, right? Either Gaussian or some exponent type, right? Now, one thing that you need to remember though is that very often basis functions are really not meant for you to actually have a hard specification of what the relationship is. Well, in some instances, maybe you already know that the relationship is quadratic or is cubic, or you have some reasonable belief that that's the case. Of course, you will choose those kind of basis functions. But more often than not, basis functions are purely used as a numerical tool, right? You typically choose a set of basis functions that are orthogonal, that can represent any function fairly efficiently, and then you just basically do a regression to get the coefficients of your basis functions to model the relationship, okay? So you can typically then the type of basis functions that you can use in this case can be a very, very large set, okay, sometimes infinite set, and then you select those basis functions based on either you truncate the basis function according to some criteria. So for example, you may say, well, I don't care about Gaussians above a certain wavelength, I'm going to throw them away, or I'm going to select some of the basis functions by using some shrinkage methods to find out which basis function actually contributes significantly to my relationship, and I also can do regularization, okay, which is what you have seen with your Rich and Lasso regression, okay?
Can I ask a question?
Yep.
For the radial basis function, what was xm?
So you are essentially, that's the mean of your feature vectors.
Oh.
So, or rather, not the mean of your feature vector, but rather the means of a set of means. So you are essentially saying that, for instance, in this case, if it is a Gaussian, that radius basis functions will be okay. So that will be one basis function, and of course you can have multiple means in which you then have and multiple standard deviations.
Okay.
Yeah. So essentially it's a set of basis functions. Okay. All right. Now, as I've shown you, there are sometimes you can linearize from physical laws that you know. So for instance, your Arrhenius relationship that I just showed you. There's also something called the Ising model, which is very popular in the literature as a simplified computational model to describe magnetic systems. Okay, so in the Ising model, basically you are trying to model the energy of this magnetic system on the lattice, and what you have is basically the Ising model is actually extremely simple. You basically have a sum of this multiplication of two terms, sigma I times sigma j. Sigma I and sigma j are basically just the directions of the spins on each part of the lattice, right? And then you have this term which depends on the energy of all your the sum of all your sigma j's. And basically what this tells you is that if your J is positive, your energy is minimized by having spins that are close together that are in the same direction, right? So if you have spin, for example, if your spin is up +1 and +1, then basically this whole term is positive, and then you have a negative of a positive term is a negative number. Now if your Jij is negative, then this variable is then optimized by having spins that are anti-parallel to each other. In other words, you want nearby spins that are up and down, right? So this is a very useful way of describing ferromagnetism and anti-ferromagnetism, right? So when J is positive, your system is actually a ferromagnet when you are at low temperatures, while if J is negative, then it tends to be an anti-ferromagnet where you actually have alternating spin to basically get a low energy, okay? And again, this is a model that is a linear model, right? It is a linear in sigma, it's also linear in sigma ij. So in other words, you can figure out the coefficients Jij from the by doing a linear regression model on these features, okay? All right. Just to show you that people actually also do something more sophisticated. So for example, one of the latest in modeling the energy of lattices is called compressive sensing for cluster expansions. They basically use something similar to the Ising model, and instead, in order to get the best model possible, they essentially do a regularization, L1 regularization. In other words, a lasso regression to basically figure out what the best set of coefficients are and what cluster of coefficients actually contribute to the energy of the system. Okay? All right. Now, one of the types of basis functions that I talked about just now that I didn't go through is piecewise polynomials. Now, this is actually a particularly important set of basis functions. Okay? Why is that? The reason is because this is something that most of you probably have done at some point during your high school or your university. So have any one of you tried to basically take Excel and say, this is my set of data points, can you fit a cubic spline through the data? Most of you have done that, right? So any one of you know how a cubic spline actually works? Okay, now I'm going to tell you how a cubic spline actually works, okay? So this is actually what happens behind the scene when you go to Excel and you say, I have X and I have Y, and I want you to fit a cubic spline through all the data points, okay? So a cubic spline is essentially what is called a piecewise polynomial. Now, what piecewise means is that, let's say you have this set of data points which are represented by the open circles right here, right? And you're essentially trying to say, well, what's the best line that I can fit throughout the data, right? Now, instead of trying to just select one function to fit through the entire set of data across the entire range, what I'm going to do instead is that I'm going to split that entire range of X into different regions. I'm going to say, I'm going to fit one function to this region, I'm going to fit another function to this region, and I'm going to fit a third function to the last region. Okay? So in other words, I have to choose some what are called knots. Okay? Each of these knots basically say, at this particular point, I'm going to choose a different function to model my data. Okay? Now, the second thing that you then need to do after you have chosen where your knots are, you then have to choose what's the order of the polynomial that I'm going to fit to each of these data points in this region, and in this region, right? Now, so of course you can do what is called a piecewise linear fit. In other words, in this region I'm going to fit one linear line. In this region I'm going to fit another, this is called piecewise constant. So in other words, I'm going to use a constant value to model my data in this region. I'm going to use a constant value to model my data in this region. and I'm going to use a constant value to model my data in this region. And when it is a constant, then the best fit is, of course, the average of the data, right? So this line is just basically the average of all the y values in this region. This line is basically just the average of the y values in this region. Now you can go for something more sophisticated. So instead of saying I'm going to only choose a constant value, I'm going to choose a linear line to fit each region. This is what you get. This is called piecewise linear. You have one linear line here, one linear line here, and one linear line here, each describing each of those regions. Okay. Now the problem with this linear line is, of course, because you don't specify the continuity at the nodes, what happens is that you have this huge jump, right? So you have a relationship that jumps from this value all the way down to this value at this node, right? And this is generally not desirable, right? So whenever we do a piecewise fitting like this, we also need to impose continuity restrictions. Continuity restrictions meaning that I want to ensure that either the value, the first derivative, or the second derivative of my at these nodes are actually continuous in values, right? So you can imagine, for example, instead of this piecewise linear, you can have what is called continuous piecewise linear. In other words, you basically have linear relationships for each of the regions, but you also ensure that at least at the nodes, each of those values are continuous with each other. Okay? So in general, whenever you choose a polynomial of degree n, you usually want all the derivatives below n to be continuous, right? So in other words, for a piecewise linear function, you want the continuity of value. For a quadratic function, you want the continuity of your value as well as your first derivative. And the most common one is the cubic spline that everyone knows and loves so well. You basically have a cubic function with continuity of the second derivative, your first derivative, as well as your value. All right, so okay, so this is how cubic splines came about. This is probably the most continuous, most commonly used. All right, so you have your data. So if you don't enforce continuity, you are going to fit a a degree 3 polynomial to each of these regions. Basically, what you get is something like this, where you have discontinuity in the values. Once you actually impose continuity of values, you actually do get that at least at the nodes, you don't see any jump in values. But here, because you're not imposing continuity of your first derivative, you see that you can actually have a huge change in gradient at the nodes as well. Okay, again, this is not desirable, right? Once you actually start imposing continuity of your first and second derivatives, then you get something that looks more and more like the cubic splines that you actually see in your Excel files. Okay, now so a natural cubic spline is basically a polynomial that is linear beyond the boundary. So in other words, you actually if you project the predictions beyond the boundaries of your data, the model actually still continues on in a linear manner. And most often what you do is that you use what is called a smoothing spline. And the way that a smoothing spline works is that it uses regularization, again that concept regularization, to control the complexity of your smoothing splines, right? So this is the loss function of your smoothing spline. So first term, again, your residual sum of squares, right? Very obvious, right? Y minus your function of x. But you see that actually you have a second penalty term, right? And what does this penalty term do? Anyone? What does it minimize? the continuity of the concavity. Yes, correct. Okay, so basically this minimizes the square of the second derivative of your graph, right? So second derivative of your graph is basically the curvature. So it is trying to not have a curve that is too bendy, okay, in essence, okay? So this is basically your smoothing spline, okay? So this is actually quite commonly used in the literature. So for example, if you are actually modeling materials, there's this atomic force field called the modified embedded atom method, okay? So people have actually used cubic splines, smoothing splines to basically fit the coefficients, fit the coefficients of your modified embedded atom method using cubic splines to basically represent these two functions f and g. Okay, so okay, let me show you the so cubic spline. I actually didn't bother to put it in the notebook, but in case you want to do cubic spline fitting yourself to any set of data that you have, you actually don't need to use scikit-learn, although scikit-learn also has cubic spline. I just want to show you that in SciPy, in the interpolate method, there is actually a cubic spline method. And let's say you give it a range of x, sine x, you just call cubic spline and you give it x and y, and then basically that fits a cubic spline to your data, and then you can use that to predict any values in between your data points. Okay? All right. Okay, I believe this is probably the final set of basis functions that we'll go through, and this is also one of the most important. So very often in a lot of scientific problems, you don't actually know what the true form of your relationship between x and y is, right? So what you essentially need is a set of basis functions that can, with whatever combination of coefficients, can model any relationship between x and y, right? So and a very common set of basis functions that are used are basically Gaussian basis functions, right? So in Gaussian basis functions, they take on this form. It's basically the exponent minus k, some constant k. This is basically 1 over 2 sigma squared, basically. X minus some mean, so essentially the mean of, you set the mean at some position, squared, okay? So these are essentially Gaussian functions that are centered at x of m, right? Now, other than Gaussian functions, there are also other similar type of functions. For example, things like the Lorentzian, the Gaussian Lorentzian, the Voitian, so on and so forth. When you actually plot them, all of them have roughly the same profile, I would say, okay? And they, of course, have certain advantages and disadvantages, okay? Now, let me show you one instance where this kind of fitting is used, okay? So, how many of you have done X-ray diffraction before? Experimentally, no. I think grad students probably definitely, but undergrads, maybe not yet. Well, sooner or later, you guys will definitely do X-ray diffraction at some point, especially if you are experimentalists, okay? So this is what you get with an X-ray diffraction pattern, right? So an X-ray diffraction pattern, you basically, what you do is that you take your sample and you shine X-ray on it, and you measure this thing that comes out of the, that's reflected from your sample, and it usually looks something like this, right? And what this looks like is basically a sum of Gaussians, right? It looks like a sum of Gaussian functions, right? So basically, when people do X-ray diffraction, the one thing that they are trying to do is to determine what is in that sample. Is this a sample of lithium oxide? Is it a sample of aluminum oxide? Is it a sample of something else, right? So the way that they do this is to basically do what is called Rietveld refinement. And in Rietveld refinement, essentially what you are doing is that you are going to fit a set of Gaussian basis functions to this measured X-ray diffraction pattern, and then you go look up in the database and compare the X-ray diffraction pattern to whatever is known in the literature, and hopefully you find, oh, this actually looks something like copper, calcium, uranium oxide 4. Okay. So this is how it works. In Rietveld refinement, you have what is called a peak shape function. The peak shape function is basically a convolution of 4 different functions. Okay. There's something for the instrument broadening. There is something for the wavelength dispersion. There's something for basically the specimen. Okay. But by and large, they are typically the basis functions that are used to model this are typically either a pseudo void or something like a Gaussian or Lorentzian function. Okay, so it is not important for you to know the details, but all that you need to know is that it is basically something like a Gaussian-like function, and then you basically minimize this weighted sum of squares. Okay, you can see this is your observed intensity minus this fitted set of basis expansion of your Gaussian functions squared. Okay. And you are essentially trying to do a least squares regression of this function before you then compare that to your database. Okay. All right. I think I'm going to skip this and skip this. Okay, actually, no, let me go back. Okay, so other than Gaussian functions, you can also use what I call wavelets. Okay, wavelets are another set of basis functions that a lot of people use. Like the Gaussian basis functions, they are also a complete orthonormal basis. And very often what you will do is that you basically use a very large set of wavelets, and then you use your shrinkage methods or regularization to basically down select to a sparse representation. So in other words, something that has very few, relatively few wavelets. And the benefits of wavelets is that they can represent both time and frequency localization very efficiently. Okay, Fourier basis typically can only do frequency localization well. So the benefit of wavelets is basically that you can do both time and frequency localization. And this set of basis function has been used again quite often in the literature for various types of materials modeling. Okay. For example, one thing that people have used this for is NMR spectroscopy. So basically what you want to do is to suppress that very large unwanted spectral line on the left. Okay, and in order to do that, basically what you do is that you do a wavelet fitting to the data before filtering off the noise and then getting back the original signal without that spectral line. Okay. All right. Similarly, you can do this for X-ray absorption fine spectra. I don't think I need to go through this. And with that concludes the extension of linear models part of the lecture. Any questions on this part before we move on?